Thank you, everyone. I'm going to talk about Wiener Filter for CMB maps using neural network, which I did with the collaboration of Claudia Scoccola and Matias Aldarriaga. So first, I will give a brief introduction. Then I'm going to talk about what is the Wiener Filter and how to apply the Wiener Filter with neural networks. And then I'm going to show the results of doing that. So as we know, the angular power spectrum of the CMB depends on the cosmological parameter of the lambda colder matter model, like the baryonic density, the colder matter density, and so on. So the study of the angular power spectrum allows us to determine the cosmological parameter with high accuracy, but reaching this level of precision requires that the data analysis being optimum in order to fully exploit the data. But the data have uncertainties which give noise to the maps of the CMB, so we need methods to reduce that noise. So the Wiener filter is a method to reduce the noise, and the output of the filter is an approximation of the original signal without noise. So the Wiener filter is usually employed with a traditional method that uses conjugate gradient, but it is a bottleneck in data analysis because the computational cost is enormous. So in this work, we study how to apply the Wiener filter with machine learning techniques, specifically with the neural network called WienerNet. So as I say, the idea of the Wiener filter is to apply a filter to noisy maps of the CMB and returns a map without noise or very close to the original signal. So we are interested in the reconstruction of the temperature distribution of the CMB. So suppose that we have a set of measurements or observation of an underlying field, which I call S, and can be modeled as a linear combination of the underlying field. And here the matrix R is a matrix response that represents the measuring procedure. And epsilon is the statistical uncertainty related to the data. So we want an estimator of the underlying field, which is a linear combination of the data, because mathematically the application of a filter to the data is a convolution. So minimizing the residual between the Wiener filter estimator and other realization of the fields gives the matrix F equal to this, where in this case S is the covariant matrix of the underlying field, and the matrix N is the covariant matrix of the noise. So this is the Wiener filter estimator. And in the case that the underlying field is a Gaussian random field, the probability density is a Gaussian distribution. So we can calculate the conditional probability for the signal given the data, which is the quotient of the joint density probability of the signal and the data, and the density probability of the data, which is proportional to the product of the density probability of the signal and the noise, because we assume that the noise is an independent Gaussian random field. So we can define the Bayesian estimator as the estimator that maximizes the conditional probability of the signal or the field given the data, and it coincides with the Wiener filter estimator defined like this. So that's why we can say that the Wiener filter estimator is optimum for the reconstruction of the signal given the data. So we studied how to apply the Wiener filter with convolutional neural networks for masked CMB maps. So a convolutional neural network is composed of two-dimensional convolutional layers in which the neurons in the layer are connected to another neurons in the previous layer inside a receptive field, and the strides is the shift between the receptive fields. So the idea is to train a neural network in order to reproduce the Wiener filter. So we need that the model learns how to relate noisy maps as inputs with the desired output, that is the original signal, given a training set as examples. So as input, we have noisy maps of the CMB, which is equal to the true sky or the signal plus the noise. And the neural network architecture is linear in the data, because we want that the prediction of the neural network reproduce the Wiener filter. And here Y represents the prediction of the Wiener filter of the neural network, and M is a matrix that is learned during the training process. So we define the loss function as the square difference between the signal and the prediction of the neural network, and the training process minimizes the expectation value of the loss function. So when the loss function is minimized or the model converges, the matrix M is equal to the Wiener filter matrix, which means that after the training of the neural network, if we make predictions with the neural network to the data, we are applying the Wiener filter to the data. So the neural network that we use is called WienerNet, which is composed of two paths: a linear path for the CMB noisy maps, which is composed of convolutional layers, and a nonlinear path for the mask, because the masks are the regions in the map where the noise is infinite and there is no signal there. And the mask breaks the statistical homogeneity, and it is not translational invariance. So that's why we need a nonlinear path for the mask with activation functions between the convolutional layers. So first we simulated CMB maps of 28 by 28 pixels and 30 arcmin of angular resolutions. We simulated the angular power spectrum of the signal and the noise with CAM, and with this we made the simulation of the maps with HELPy. And we used the approximation of flat sky and homogeneous noise, in which the noise is the same for all the pixels. So we trained the neural network with these maps, and after training, we make predictions with 300 maps. And this is an example for one of these maps. This is the map of the signal. The second one is the map of the signal plus noise. And the third is the prediction for that map. Then we calculated the difference between the pixel intensity of the signal and the prediction of the neural network for the same map. And we made an histogram, and we found that the mean is equal to 0.29 and a standard deviation of 56.24. Then we made a comparison with the result of making the Wiener filter with the conjugate gradient method that I say it is a bottleneck. So we made a plot of pixel intensity. In the signal, in the abscissa axis, it is the pixel intensity of the signal, and in the vertical axis, it is the pixel intensity of the prediction of the neural network. And we did the same for the result of making the Wiener filter with conjugate gradient method. And we found that both plots have the behavior of a straight line. Then we calculated the difference between the pixel intensity of the neural network prediction and the conjugate gradient results, and we made an histogram in order to calculate how much the results differs. And the mean is equal to 0.29 and a standard deviation of 25.02. And the behavior is a Gaussian distribution. So then we calculated the standard deviation distribution of the difference between the signal and the results of making the Wiener filter with the neural network WienerNet, and making the Wiener filter with the conjugate gradient method for 300 maps. And we calculated the mean of the standard deviation, and we found that both methods have very, very similar means of the standard deviation. So this we can say with all these results that making the Wiener filter with the neural network give results that are very close to the results that we expect with the conjugate gradient method. So then we study the efficiency of WienerNet respect to the conjugate gradient method. So we simulated maps of 56 by 56 pixels, 128, 256, and 512 pixels. All of these with the angular size of the map of 10 degrees and 3 scales of homogeneous noise.
Then you have 5 more minutes.
Okay, thank you. So we calculated the computing time of making the Wiener filter with the neural network WienerNet and making the Wiener filter with the conjugate gradient method. And in the case of the Wiener filter with neural network, we found that for 56 pixels, the computing time is the order of 1 second, and for 512 is the order of 1 minute. And in the case of the Wiener filter with the conjugate gradient method, we found that for 56, the computing time is the order of 1.5 seconds. For 256 is the order of 2 hours. And for 512 is the order of day. So with all these results, we can say that making the Wiener filter with the neural network is faster than making the Wiener filter with the conjugate gradient, that I say it is a bottleneck in data analysis. The results of making the Wiener filter with the neural network are as good as we expect that the results with the conjugate gradient method. So as a future work, we want to apply the neural network to CMB polarization maps, and we want to make an extension of the WienerNet to inhomogeneous noise, and we want to make an implementation of the neural network to several subfrequencies of the CMB maps as that can be produced by the cubic experiments. So, thank you.
Thank you very much, Belén. So, are there questions here, the audience? Questions here? Yes.
Hi. And are there, appreciable differences between the predictions by machine learning and the traditional conjugate gradient method? Are there error distances?
Sorry, what is the big difference between the results? Are you asking?
Yes, if the predictions of the underlying field differ in some way, or the results are consistent.
Okay. The big result that I present here is that making the Wiener filter with the neural network reproduce results that are very similar to making the Wiener filter with the conjugate gradient method. So there are no big difference in the prediction of the neural network with respect to the result of making the Wiener filter with the conjugate gradient method. That's why we are interested in this neural network, because the results are good and it is faster than the traditional method, that it is very is a bottleneck in the data analysis.
Okay. So we thank Belén again.
Okay, thank you. Thank you, everyone.